Hello everyone, today I'm going to introduce ABNDP, co-optimizing data access and load balance in near data processing. Near data processing is one of promising paradigms to optimize memory access cost. By moving computing logic near data, the memory accesses can be done with lower latency, lower energy consumption, and higher bandwidth. There are various memory technologies to realize NDP, including adding computing logics inside DRAM banks, inside the logic die of 3D stacked memories, or to the buffer chip of DDR DIMMs. In this work, we focus on 3D stacked memory-based NDP architectures. Typical stacked memory products include HMC and HBM. In such an NDP system, there are multiple memory stacks connecting with each other and form a memory network. In a memory stack, there are multiple NDP units connected by the intra-stack memory network. Specifically, an NDP unit consists of local memory and a computing logic. In HMC, we call each vault together with its own computing logic as an NDP unit, while for HBM, we call each memory channel with its computing logic as an NDP unit. So the system can be regarded as massive NDP units operating independently and in parallel. From now on, we will abstract away the detailed physical differences between technologies and focus on the logical NDP units. Unfortunately, there are two issues in such NDP systems. The first one is a high remote access cost. In NDP systems, data are partitioned among all the units. Here is a computing task that touches data 1 to 3, which are stored in other units and require remote accesses, incurring extra latency and energy cost. The second issue is a load imbalance. To fully utilize a massive parallelism in NDP systems, we need to assign tasks to all NDP units with balanced loads. This is sometimes quite challenging. First, loads of different tasks can be drastically different, and the performance of a task depends on the location of the executing unit. Running task 3 is slower than task 1, since task 3 are farther from data. What's worse, there exists a fundamental trade-off between the two issues. To reduce remote access cost, we should assign tasks based on data locations. In the figure, many tasks need to access data 1, which means data 1 is a hot data. Assigning tasks based on data locations will schedule too many tasks to or near that unit, creating a new hotspot and causing load imbalance. As for load imbalance, we could use dynamic scheduling techniques such as work stealing to balance loads. In the figure, the yellow bars show the workload on each unit. Then, the tasks should be scheduled to this idle unit. To do so, tasks are moved further away, increasing remote access cost. Therefore, the fundamental trade-off makes it hard to co-optimize the two issues. Improving one usually sacrifices the other. In our work, we try to co-optimize the two issues with dynamic data caching and computation scheduling. We adopt a task-based programming model for more flexible data and computation scheduling. We propose a distributed DRAM caching scheme called Traveler Cache to reduce remote access distances and offer more near-data locations for scheduling. Then we propose a hybrid scheduling policy that considers both remote access and load balance. First, let's take a look at the task-based model. We observe that NDP-friendly applications are composed of data element-wise parallel tasks. For example, suppose we're running PageRank on this graph. The application is composed of the PR value updating of each vertex, and the PR value updating of different vertices can be done in parallel. Thus, it is natural to use a task-based programming and execution model in NDP architectures. We adopt a model similar to existing work. Tasks can spawn child tasks dynamically by calling the enqueueTask API, and we use a box synchronization model to simplify coherence control. We further encapsulate a hint to each task. A hint includes the access data addresses of the task and an estimated computation load. The information are used for caching and scheduling, as we will introduce later. In our work, tasks are the basic unit for flexible scheduling. Now we introduce a baseline hardware architecture. Here is a network of NDP units. This shows a traditional NDP unit architecture. There are two cores in each unit with their L1 cache. They can access the local DRAM and communicate with other units via the router. To support task-based execution, we add a task queue and a task scheduler. And since we have the data access information encapsulated in hints, we add a prefetch unit to fetch data in advance to the prefetch buffer. This is a workflow of task-based execution. Tasks are generated by the cores of the unit. The task scheduler moves tasks into or out of the queue dynamically, and reserve a prefetch window in the queue. As the execution proceeds, the task is moving forward. When it enters the prefetch window, the task queue will pass the hint metadata to the prefetch unit for prefetching. And finally, it will be fetched by the core to be executed. Notice that this is a workflow running in each ADP unit distributedly and in parallel. ABNDP is built upon the baseline architecture. We propose two optimizations. The first one is traveler cache. We reserve a small portion of the DRAM as cache to reduce remote accesses, and we propose an efficient text scheme stored in SRAM to record caching information. Then we propose a hybrid scheduling policy that co-optimizes load imbalance and remote access cost. We reserve a scheduling window in the task queue. For tasks in a scheduling window, the scheduler will choose the best unit for it to be executed. Now introduce the details of the two optimizations. Traveler cache is a distributed DRAM cache scheme. We use a small portion of local memory to cache remote data. There are a limited number of locations that the data can be cached. We call them camp locations. We first divide the units into 4 groups, and there is one camp location in each group except the memory location. In this example, the camp locations of the read data is shown in the figure. As we can see, the camp locations of the data is limited. The requests can be served by a nearby camp location. In this way, we can improve the cache utilization. A camp location is a pair of unit ID set ID, representing a specific cache site in a specific ADP unit. It is done in cache line granularity. The mapping of a camp location in a group is computed only using the physical address. This deterministic mapping can reduce metadata cost, as we will introduce in the next slide. The set ID is quite easy. We just use the bits in the address directly. For unit IDs, we use a skewed mapping that uses different bits in the address as unit IDs in each group. For this read data, we use this part as unit ID 0 and generates this camp location, and another part as unit ID 1 and another as unit ID 2. This skewed mapping can reduce cache conflicts. What's more, it enables better scheduling opportunities. For example, suppose we need to access the red data and green data together. The distances of them in each group are different. There may be a group that they are quite near. This is a better unit to execute the task. The tag for cache data is challenging in ADP systems since the area for SRAM on the large die is quite limited. For information of local cache data, we propose a novel tag scheme with reduced size thanks to the deterministic mapping. Here we omit the details and please refer to the paper. We only present the result, which is 160 kilobytes for each ADP unit. And we do not keep tracks of data cached in other units. Instead, when the data is needed, we probe the nearest camp locations. If it is present, the data is returned directly. If not, the request is relayed to the memory location. To sum up, the limited camp locations can make more efficient use of cached data. The deterministic mapping saved metadata overhead, and skewed mapping reduces cache conflicts and enables better scheduling opportunities. As for scheduling, we design a scheduling policy that considers both remote accesses and load imbalance. For task T, the scheduler computes scores for all units U and chooses the unit with the lowest score. The score is composed of 2 parts. The first part is a memory access score, depending on data access distance. The second part is a load imbalance score, computed using the sum of estimated workload in the task queue. The formula means that we gave a discount to idle units, so even if they are a little far from data, tasks can still be scheduled to them. The weight means maximum distance that can be overcome due to load imbalance. We set it to half of the diameter of the system. Here is our methodology for evaluation. We simulate the NP systems using ZSIM. Our system includes 16 memory stacks, 128 NP units. For scheduling, we evaluate the scheduling method considering remote access and load imbalance separately, and our hybrid scheduling policy. And we evaluate the traveler cache alone. Lastly, we combine hybrid scheduling and traveler cache to see the overall results. We implement 8 representative NP-friendly applications using our task-based model. Here is the results. This figure shows the overall speedup. The figure on the bottom left shows the remote access cost. We count the total hops needed for remote accesses. And the figure on the right shows the workload distribution on each NDP units. The x-axis has different units, and we sort the workload from smallest to largest. If the curve is more skewed, it means imbalance, and more flat means balance. We use one application, PageRank, in the bottom two figures to show the details. If we assign tasks based on data locations to reduce remote accesses, the hops are reduced slightly. Well, the load imbalance issue becomes more severe, which hurts overall performance. And if we use work stealing for load imbalance, overall performance is better due to balanced loads, but it incurs much more remote accesses. Our hybrid scheduling incurs less remote accesses than work stealing. Thus, the performance is the best, but it still causes significant remote accesses than the baseline. This shows the benefits of Traveler Cache. It can reduce remote accesses by 21%, but the load imbalance issue remains since it is not considered in Traveler Cache. Lastly, we evaluate the combination of Traveler Cache and hybrid scheduling. Here is the result of applying them separately, and our overall design achieves 1 times 68 times speedup, which is the highest. The load is balanced among units, while only 9% more remote accesses are introduced than the baseline. We can see that the result is better than simply adding the two optimizations. This is because they are co-designed with each other. The caching can enable better scheduling opportunities for the hybrid scheduling to utilize. To sum up, we observe that there exists a fundamental trade-off in NDP architectures between minimizing remote accesses and achieving load balance. We propose two optimizations to solve the two issues. Together, ABNDP simultaneously alleviates two issues without making trade-off. Thanks for your listening.